In this section, we're going to look at improper integrals. It's basically the reason that we spent so much time looking at limits again, in the middle of our chapter on integration. Most of this chapter has been on techniques of integration, what kinds of substitutions will work, or, algebraic tricks to rewrite it using partial fractions, things like that. Now we're going to look at special kinds of integrals. These are ones that are they look like and kind of behave like definite integrals. So there are limits on the integrals. But the reason they're called improper is because either it could be that one or both of the limits of integrations are infinite, or it could be that the integrand has an infinite discontinuity somewhere in the interval of integration. And an infinite discontinuity, that basically means like a vertical asymptote. So, for example, these two integrals right here, these are both improper integrals, and the reason just sort of really stands right out, right? That I'm integrating from 1 to infinity, that one, so it's got an infinite limit. Infinity is not a number, that makes this improper. This one, they're both infinite limits. I'm integrating that over the entire whole real number line. So that's an improper integral. Infinity is not a number. We can't plug in infinity. What we can do is take a limit as x approaches infinity. So you can see why we spent some time working with limits in the last section. They're going to come into play here. And then, for these other two examples, the first integral, we're integrating from 1 to 5, and our integrand is 1 over the square root of x minus 1. So look, this is not continuous at 1, and 1 is one of our limits of integration. So discontinuous at x equals 1, and that's one of our limits. That makes it improper. If you look at this other one, you might say, well, look, that's not discontinuous at either of the two limits. And you're right, it is definitely continuous at 2 and negative 2, but it's discontinuous at x equals negative 1, and negative 1 is in the interval from negative 2 to 2. So we're gonna begin, I think, just with an example, and we're gonna think about an example that isn't really improper yet. All right. So let's think about the definite integral from 1 to b. So imagine b is just any number that's bigger than 1, right? But some number, and I'm integrating from 1 to b the function 1 over x squared. Here's kind of a visual, conceptualization of this limit. I think of it as an area under a curve. It's the area under the curve, 1 over x squared, starting at 1 and just ending at just some value b. Here we've drawn it so that b is between 2 and 3, but that could be anywhere. You just stop wherever, call it, that's our value b, and that defines some area. That's what this integral gives us. So let's evaluate this integral, this definite integral. And I'm going to start by rewriting it. Instead of 1 over x squared, I'll write it as x to the minus 2. Because, of course, that's easier to integrate. This is a power rule integral. And if we integrate x to the minus 2, we get negative 1 over x that we're evaluating from 1 to b. And we plug in the upper limit first. Negative 1 over b minus a negative 1. So it'd be a plus 1, or I guess we could write it as 1 minus 1 over b. So look, for any place that we actually stop, right? If we stop at some arbitrary value b, that's going to be the area. So I could use that as a formula to say, okay, let's say I want the area from 1 to 10. Let's say I want the area from 1 to pi. Maybe I want the area from 1 to, I don't know, 568. I could just plug in that upper limit for b in this expression and get that area. Now, consider the fact that we don't want to stop at all. Let's say I just want to keep pushing b out to infinity. I'm going to keep picking up more and more area. But as you go, this function is approaching 0. As you keep going, you keep picking up more and more area, but you keep picking up like littler, like smaller and smaller bits, right? The additional area you pick up is smaller and smaller. So what happens to the total area? To figure that out, we're going to let b approach infinity. And that'll give us the total area under the curve, starting at 1 and going out forever on the graph. So here's how we handle this improper integral. It's an integral from 1 to infinity, 1 over x squared dx. This is, first we rewrite the integral as a limit. This is a limit as b approaches infinity of the integral from 1 to b. We rewrite it as the limit of a definite integral that we can evaluate. And of course we did the integration on the previous page, so we're not going to repeat that. So this is the limit as b approaches infinity of 1 minus 1 over b. And as b approaches infinity, this whole thing approaches 1. So that total area under the curve is limited. It's going to keep getting bigger, but it's going to get bigger, like if I were to graph, like if I could chart a graph of like the area, depending on where we stop, it would keep approaching 1. It would be limited. So like keep increasing, but not very fast. So if we have infinite limits of integration, this is our basic approach. We've already seen, the one we just did, that's case 1. It could be that our lower limit is negative infinity. And then we're going to evaluate the limit as a approaches negative infinity of the definite integral from a to b. It's basically the same scenario as the first one, right? It's just that it's the lower limit you replace. If they're both infinite, what you have to do is pick some value c, pick that value based on what seems convenient. Any value will do as long as the function's continuous there. And you split it up into 2 integrals, from minus infinity to c, and then from c to infinity. This is case 2, so you set up a limit for that one. This is case 1, so you set up a limit for that one, and then combine them. Let's do another example. This is similar to the last one, right? I mean, the function's similar. It's 1 over x instead of 1 over x squared. And we're still integrating from 1 to infinity. And in fact, even their graphs look kind of similar, right? They do something like this. And I just want to go out forever and see what happens. All right, so first, we rewrite this integral as the limit of a definite integral. The limit as b approaches infinity of the integral from 1 to b, the definite integral, 1 over x dx. Now that's no longer a power rule integral. It's 1 over x, so that's a log rule. So this would be ln x from 1 to b. I didn't bother with the absolute value signs when I integrated this time because we know that what we're plugging in, we're limited to positive values on x anyway. So we're going to plug in our limits of integration. And this is ln b minus ln 1. Now ln 1 is a constant. Ln of 1 is equal to 0. But ln of b, as b approaches infinity, I'm going to let the argument inside the ln function get huge. You'll remember from the last section, we know that this grows without bound. It doesn't grow very quickly, but there's no upper limit, right? It just keeps getting bigger without bound. And so this improper integral is infinite. So look, we had 2 different behaviors, 2 different results. Now I'm going to compare these 2 results here. I'm going to go back to the first one. This improper integral gave us an actual value. It had a limit, and it was 1. So we say that this integral, this improper integral of 1 over x squared from 1 to infinity converges. I know it converges because I evaluated it and saw that it approached a number. So that integral converges. If an improper integral does not converge, if I go through this process and it does anything other than approach an actual fixed value, then we say that this integral diverges. So one way that an improper integral can converge is that it just blows up, right? Like this one. It approaches infinity. Let's do another example. This is an improper integral because it has an infinite limit. This time we're integrating the sine function from 0 to infinity. So we start by rewriting the integral as the limit as b approaches infinity of the definite integral from 0 to b. We know how to do this integral. The integral of sine is negative cosine. Now I'm going to plug in the limits of integration. So we've got negative cosine of b minus a negative, so plus cosine of 0. Cosine of 0 is equal to 1. So this is the limit as b approaches infinity of 1 minus cosine of b. All right, now let's see what happens. You know, if we let b grow without bound, well, what happens to the cosine function? I mean, when you think about the cosine function, one of the first things you might, the images that appear in your mind is the graph of a cosine function. And the cosine function is periodic, right? It looks like this, and it just keeps going like that forever. It doesn't settle on a value. It doesn't converge to a single value. The cosine of b does not approach a limit. And so since we don't get a numerical value, like this limit, it doesn't settle on a value, it's not getting closer and closer to a single value, this improper integral diverges. So, there's a couple ways that an improper integral can diverge. It can diverge the way we saw the last example, in that it blows up, goes to infinity. Or it could diverge because it just sort of like oscillates, or like just keeps moving around. It doesn't settle on a value at all. Let's do another one. We're going to evaluate this improper integral from 1 to infinity of 1 minus x times e to the negative x. Now, when you're evaluating an improper integral, we know that we start, right, by rewriting this as the limit, as in this case, as b approaches infinity, of the definite integral from 1 to b, 1 minus x e to the negative x. But certainly what involved in this process is being able to integrate this function, right? So this isn't just one of the basic forms that we know, like the ones that we just did, like the 2 or 3 examples we just did. But we do have a technique, and we think back to what we learned in this section. We can use integration by parts on this integral. So I'm going to do this on the side. And I'm going to let u equal 1 minus x, so that du is equal to negative dx. I'm going to let dv equal e to the negative x, and that means that v is equal to negative e to the negative x. So the indefinite integral, 1 minus x times e to the negative x, is u times v minus the integral v du. So let's see how this shakes out. U times v. I'm going to multiply these two. So negative e to the negative x times 1 minus x minus the integral of v du. So the integral of negative e to the negative x dx. Alright, I'm gonna, minus the integral of positive. That's minus a minus, so like, that'll be a positive there. V times du. E to the negative x dx. Alright, now this integral we know how to do, right? The integral of e to the negative x is negative e to the negative x. And because of this negative outside, that'll turn into a plus e to the negative x. Plus a constant, since I'm writing this as an indefinite integral. And then I'm just going to, let's simplify a bit. I'm going to, I guess, maybe distribute this first factor of e to the negative x. So we have negative e to the negative x plus x e to the negative x, and then plus e to the negative x plus c. We can cancel those terms. So we get, x e to the negative x plus a constant. Alright, so this is the result of just how we integrate that as a function. Now let's use that result. So this is equal to the limit as b approaches infinity of x times e to the negative x from 1 to b. And now we can plug in the limits. I think actually what I'll do first is rewrite that. E to the negative x, I'm going to write that as a division and put the e to the x on the bottom. So plugging in the upper limit first, we get b over e to the b, minus, plugging in 1, we get 1 over e. So 1 over e, that's a constant. So now we just have to figure out, what is happening, right? What's happening to b over e to the b? And that we can find by using L'Hopital. We can use L'Hopital because b approaches infinity, e to the b approaches infinity, so that's an infinity over infinity type. The limit as b approaches infinity of b over e to the b is equal to the limit as b approaches infinity of 1 over e to the b, just, taking the derivative on top and on the bottom. And now as b approaches infinity, this approaches 0. That means that up here in this limit, this piece approaches 0, and so overall this whole limit is negative 1 over e. Alright, let's try another one. This one's going to be a little bit more work maybe just because both the upper and lower limits are infinite here. So we're going to do two things to set ourselves up. One is we got to pick a value somewhere in the interval of integration, so that means any real number. You can pick any real number you want, but for the sake of convenience, because I think it's easy to plug into things, I'm going to pick 0. So I'm going to rewrite this as the integral of minus infinity to 0. And then the integral from 0 to infinity. Should make my e's look like e's. Now each of these improper integrals I'm going to rewrite as the limit of a definite integral. So the first one, this will be the limit as a approaches negative infinity of the integral from a to 0. And then this next one is the limit as b approaches positive infinity, 0 to infinity. Okay, so now I think what's next to keep working through this integral is to figure out how we integrate e to the x over 1 plus e to the x. And a little bit of playing around will, I think, reveal pretty quickly that this is an arctan form, right? So one thing that's important to realize is that e to the 2x is e to the x squared, right? I mean, when you raise a power to a power, you multiply those exponents. So that's the square of e to the x, and the derivative of e to the x is e to the x. So if we let, I'm going to do this kind of off to the side here. If we let u equal e to the x, then du is e to the x dx. And so that means that the integral of e to the x dx over 1 plus e to the x squared is the integral of du over 1 plus u squared. And that's an arctan form, where a is equal to 1. So this is just arctan of u plus a constant, or arctan of e to the x. So that's what we're going to use now here. So this is the limit as a approaches negative infinity of arctan of e to the x from a to 0 plus the limit as b approaches infinity of arctan e to the x from 0 to b. And I just realized on the top line, in the middle line here, that was supposed to bring down a b there. Okay, now we can plug in our limits of integration, and pretty soon we'll be ready to evaluate the limits. So we have arctan of e to the 0 is 1 minus arctan of e to the a power plus the limit as b approaches infinity. Arctan, upper limit first, arctan e to the b minus arctan of e to the 0, which is 1. So notice this will happen in these improper integrals where we have to split it up. Like we here, I chose 0 to split it up. So in both of these limits, when I'm plugging in my limits of integration, right, I have this arctan of 1. There's a positive arctan of 1, and then here's a minus arctan of 1. we could carry it through, but these are actually going to cancel. They're constants, and they cancel, right? They're both equal to pi over 4. So let's see what happens. As a approaches negative infinity, see what happens with these other terms. As a approaches negative infinity, e to the a is approaching 0, because that would be an exponential decay, right? That exponent is approaching negative infinity. And arctan of 0 is 0. So this whole thing is approaching 0. As b approaches infinity, e to the b approaches infinity, right? That's exponential growth. And arctan of an argument that's approaching infinity, we're going to have to think about that a little bit, because arctan does not blow up as the argument blows up. So, as arctan, if arctan, I'm going to do a little bit of work in the margin up here. We're trying to figure out what happens to arctan of, I don't know, x as x approaches infinity. So remember that the arctan is the inverse trig function, right? So it says if, like for example, arctan of 1 says give me the angle where tangent is equal to 1. So if I'm thinking about arctan of infinity or arctan of something approaching infinity, what I'm really doing is trying to figure out what does, let's say I'll call it theta, approach to make tan theta blow up, right? Get huge. Because that's what we're saying when we talk about arctan of infinity. We're saying that the tangent function is blowing up, and we want to know what angle makes that happen. So if we look at the unit circle here, remember that tangent is sine over cosine. So the only way to make a fraction blow up, there's two ways. One is that the numerator could blow up, but we know that doesn't happen because sine is bounded, right? Sine is never bigger than 1 or never less than -1. So the only other way to make a fraction blow up is if the denominator approaches 0 and cosine approaches 0. That happens at the top of the circle. That's where the x-coordinate is 0. So that's at pi over 2. So that was sort of just a little bit of work to figure out or convince ourselves why, understand why the arctan, this piece, approaches pi over 2. So we have the arctan of 1 terms cancel out. The arctan of e to the a, that approaches 0 as a approaches negative infinity. And then this other term, the only thing we're left with is pi over 2. All right, so the next thing we're going to look at are improper integrals that have an infinite discontinuity. Essentially, you know, that means that there's a vertical asymptote. If you were looking at a graph of the function. Like there's some value in the interval of integration that makes the function blow up, either to positive infinity or negative infinity. So if we're looking at, suppose we're looking at, you know, say here's the real number line, right? And we're integrating on the interval from a to b. If there's an infinite discontinuity at b, right? So like if that's the value that makes it blow up, what we're going to do is rewrite that improper integral as the limit of a definite integral. And it's going to be the limit as, say, c approaches b from below. I have to approach b from inside the interval, right? So my interval is from A to B. I have to approach B from below. So, so we evaluate that limit. If the infinite discontinuity is at the lower limit, if it's at A, then I rewrite the improper integral as the limit of the definite integral as C approaches A from above. Again, I have to approach A from within the interval of integration, and we evaluate that limit, just similar to how we did those infinite limits, or the limits as x approaches infinity. Now, let's say there's an infinite discontinuity somewhere in between, right? Somewhere inside, not at one of the actual limits, but somewhere inside, say at some value c. What we do then is split up the integral. I have one integral from a to c, and I have to set that up as a limit approaching c from below, and then I add that to the integral from c to b, but with that integral I have to approach c from above, because that has to be inside that interval of integration. And then each of these, right, each of these integrals we approach using cases 1 and 2 above. Let's do an example here. We're going to integrate from 0 to 1 the function 1 over the cube root of x with respect to x. This is improper because there's an infinite discontinuity at 0. That 0 limit of integration there, that's the problem. So I'm going to rewrite this as the limit as c approaches 0. It has to approach 0 from inside the interval, so that means from above. I'm going to rewrite the function as x to the minus 1/3, and now my limits are c to 1. We can integrate this function, it's not too hard. It's a power rule integral, so that'll be x to the positive 2/3 times 3/2 from c to 1. So this is the limit as c approaches 0 from above. And we have 3/2 times 1 to the 2/3 power minus 3/2 times c to the 2/3 power. Now, as c approaches 0, c to the 2/3 power approaches 0, so this whole thing is approaching 0, and that means we're just left with 3/2 times 1. Let's try another one. Here we're going to integrate the function from 0 to 2, 1 over x cubed with respect to x. So again, same problem as the last one, right? There's an infinite discontinuity at 0. So we're going to rewrite this as the limit as c approaches 0, again from above. It has to be from inside the interval. And we're going to integrate from c to 2 the function x to the minus 3 with respect to x. That's another power rule integral, so I think we have a good handle on this. Integrating x to the minus 3, we'll get x to the minus 2 times a negative 1/2. I'm going to rewrite this first before I plug in my limits. I'll say that's a negative 1 over 2x squared from c to 2. If we plug in, let's see, the upper limit comes first, so that'll be 4 times 2 is 8, so that'll be a negative 1/8 minus a negative. I'll write that as a plus 1 over 2c squared. Now c, so the negative 1/8, right, that's a constant, that's staying put, so I'm not going to worry about that. As c approaches 0, This is a fraction where the numerator is fixed, the bottom is shrinking, getting smaller and smaller, approaching 0. So that means the whole fraction has to blow up. And so this whole limit is in fact infinity. That means that the improper integral diverges. All right, let's try another one. So the introduction here says that it's doubly improper. So let's figure out why. I mean, one reason it's improper jumps right out. It's got an infinite limit, right? We're integrating from 0 to infinity. So I know that that's going to be an issue. But the other problem is that it is there's a infinite discontinuity at 0. And of course, then there's the infinite limit. So we have to approach these two problems kind of separately. I mean, we can kind of do them, I guess, in parallel. But there's an infinite discontinuity at 0, and there's a infinite limit of integration. I can only apply one limit at a time, right? So what we're going to do is actually split up the interval at a convenient spot. And for convenience, I mean, usually I'm just thinking what's going to be nicer to plug in when we have to actually evaluate. I'm going to pick 1, I think, because 0 is no longer convenient. There's an infinite discontinuity. So I'm going to rewrite this as the integral from 0 to 1 plus the integral from 1 to infinity. Now, each of these integrals is only improper for one reason, and that's good for us. So we're going to set up the limits that we need for each of these. The first one, right, that's improper at 0. So I'm going to set this up as the limit as c approaches 0 from above, from inside the interval. The integral from c to 1 over root x times x plus 1 plus the limit as b approaches infinity. The integral from 1 to b of 1 over the square root of x times x plus 1. Alright, so we've split it up. We now have set up separate limits, right, that we need to evaluate. But our next step now is, we're stuck until we actually integrate this function. So we have to think about how we can integrate this function. So I'm going to do some of this off to the side. We're looking at 1 over root x times x plus 1. This can be done if we let u equal the square root of x, or I'll write it as x to the 1/2 power. And if u is x to the 1/2 power, then du is 1/2 x to the negative 1/2 power. So now I'm going to use a little bit of algebra to rewrite this, because at first it might not seem all that obvious, but I'm going to, rather than think of this as a u in the denominator here, I'm going to throw that up in the top as x to the negative 1/2. And on the bottom, that x is the square of the square root of x. Now I almost have du up there. I'm off by a factor of 1/2. I'm going to throw in a factor of 1/2 here. compensate with the 2 outside. Now I'm going to rewrite this with u's. So up top we have du. On the bottom we have 1 plus u squared. So maybe that form is looking a little bit familiar. This is the arctan form. So this result is just arctan u, or 2 times arctan u. And for us that's 2 times arctan of root x plus a constant. So that's what we're going to use over here in the limits that we set up. So we've got 2 arctan of root x. And then our limits here are from c to 1. And then we'll do the same thing here with our limits being from 1 to b. All right, now we can plug in our limits of integration. So 2 arctan of root 1 minus 2 arctan of root c plus the limit as b approaches infinity. 2 arctan of root b minus 2 arctan of root 1. Now finally, we're getting close, right? We're ready to evaluate some limits. So again, I'm just going to point out here we have a positive 2 arctan of root 1 minus 2 arctan of root 1. Those guys cancel, so I don't have to worry about those. As c approaches 0 from above, so approaches 0 using positive numbers, this first arctan is approaching arctan of 0, so it's approaching 0. And of course 0 times 2 is still 0. The other arctan, as b approaches infinity, the square root of b also approaches infinity, and so the argument inside of arctan is blowing up, and we know from what we did a couple, two or three examples ago, that this arctan is approaching pi over 2. So, and of course there's still a factor of 2 there. So this limit is equal to, and in fact maybe I should bring these down. I kind of canceled out the 2 arctan of root 1 right off, and those do cancel, but maybe I'll just sort of evaluate them, bring everything down. The first one approaches 2 times arctan of 1 is pi over 4 minus 0 plus this other limit is 2 times pi over 2 minus 2 times pi over 4. So those still cancel, and we are left with just 2 times pi over 2, or pi. All right. Next, we have just a theorem, like for a certain kind of improper integral. Just kind of summarizing things we know. And this theorem isn't anything we really need, right? Like we already know how to evaluate these integrals. If p is equal to 1, it ends up being a log rule integral. And if p is any other value, it's a power rule integral. And then we just evaluate the limits. But what you'll notice is that if p is strictly larger than 1, the integral from 1 to infinity of 1 over x to the p converges, and it converges to that value, 1 over p minus 1. If p is less than or equal to 1, it will diverge. And it will diverge in a way that it blows up. So, for example, the integral from 1 to infinity of 1 over x squared, using this theorem, says this should be 1 over 2 minus 1, because p is equal to 2 here, which is 1. And we actually already figured that out. That was the very first example that we did in this section. On the other hand, if we compare that to the integral from 1 to infinity of 1 over root x, we could rewrite this as the integral from 1 to infinity of 1 over x to the 1/2. I'm writing it in that way. I'm not writing it as x to the negative 1/2. I'm writing it as 1 over x to the positive 1/2 because I want it to be in the form that this, in this particular form, so I could apply the theorem. Now this integral diverges because in this case p is 1/2, and that's less than or equal to 1. But again, it's something that we could do. I mean, the integration itself is not difficult. All right, we're going to finish this section with one last, kind of biggish example, but it's a good one. We're going to look at this figure which we call Gabriel's horn. So Gabriel's horn is formed by taking the region that's bounded by the function y equals 1 over x, right? So like that's this curve right here, and x equals 1, and then going out to infinity. So this does not end. This extends indefinitely, and then revolving that about the x-axis. So the first thing we're going to do is just find the volume of this, right? So obviously Gabriel's horn cannot actually exist, right? It has infinite length, so it cannot exist. But this sort of theoretical object, we can calculate its volume for sure. So, and you could do that using the disk method, right? So let's say we draw this rectangle. Vertical rectangles work well. This is a delta x width. And when you revolve this, right, you get this nice disk with the radius is equal to 1 over x. So the delta v pi r squared h is pi times 1 over x squared delta x. And so that means we can find its volume. The volume is pi times the integral from 1 to infinity, 1 over x squared dx. And we could certainly do the integration ourselves, but we'll note that we could also use theorem 11, and just for the sake of time, for the sake of brevity, I guess, I'm going to go ahead and just use theorem 11. Theorem 11 says that this is going to converge because p is equal to 2, which is greater than 1, and this converges to pi times 1 over 2 minus 1, which is equal to pi times 1, or just pi. So it has finite volume. This figure that has infinite length actually has a finite volume. Now let's consider the surface area. The surface area, you can see that the integral is given here. That just comes directly from the surface area integral formula from the last chapter. And so I'm going to, of course, pull that 2 pi outside times the integral from 1 to infinity, 1 over x times the square root of 1 plus 1 over x to the 4th. Now we cannot use theorem 11 on, unfortunately. This is going to take a bit of doing, so be patient. We're going to use some algebra to rewrite it, and then I think I'm actually going to end up referring to, once I'm able to rewrite it a bit, refer to one of the tables, formulas in the tables. Alright, so the first bit, I'm going to rewrite this, of course, as a limit of the definite integral from 1 to b. And while I'm at it, I'm going to rewrite the stuff in the fraction, in the root. I'm going to write that as a single fraction. Once you get a common denominator, which is x to the 4th, up top we have x to the 4th plus 1. This x to the 4th in the radical in the bottom, we're going to pull that out as a 1 over x squared. And so when we have that factor of 1 over x squared out there, it's going to buddy up with that 1 over x factor, so we've got 1 over x cubed. I'm going to write this as the square root of x to the 4th plus 1 over x cubed. Now, here what we're going to do is we're going to let u equal x squared. And if u is equal to x squared, then du is equal to 2x dx, and u squared is equal to x to the 4th. Let's see. So yeah, so du is 2x dx. I'm also going to take this and rearrange that equation to get dx. So dx is du over 2x. So let's see what we got now. 2 pi times the limit as b approaches infinity. The integral, let's see, x equals 1 to x equals b. What we have here is the square root of, let's see, u squared plus 1. Now, I'm going to do something that's going to seem weird, but I'm going to fix it right away. I'm going to mix my x's and u's in the same integral, but I'm going to fix that post haste. So I've got an x cubed in the bottom. My dx is du over 2x. So now, I know you're as anxious as I am to fix this issue of x's and u's in the same integral. So here's what I'm going to do. I'm going to yank this out as a factor of 1/2 outside. So that's gone. And then look, we have x cubed times x. That's x to the 4th. And that's equal to u squared. So now when we pull out that pulling out that 1/2 will cancel the factor of 2 out in front, so now we just have a factor of pi. And we have the integral x equals 1 to x equals b. And this looks like the square root of u squared plus 1 over u squared du. Now this is a form that at least we could kind of look up in the table. I have a feeling maybe a bit more slogging through, we might be able to do this with trigonometric substitution, just because of that radical that appears. But just to kind of get to the result a little bit quicker, I'm going to invoke formula number 30, I think. So I'm going to do a couple things here. First, I'm just going to rewrite the integral so we can look at it, and then we have some more space to keep working. So formula 30 in the table in the back of our text says that the integral of the square root of u squared plus or minus a squared over u squared is negative radical u squared plus or minus a squared over u plus ln absolute u plus the radical plus c. And of course that's the same radical that appears. I'm just running out of space, so I'm kind of shortening this a little bit. So let's apply this. So it's the limit as b approaches infinity of, so we have negative radical u squared plus a squared. So u is equal to x squared, so this would be x to the fourth plus 1, a is equal to 1, over u, that's over x squared, plus ln of absolute x squared plus the radical x to the fourth plus 1, from 1 to b. And we're going to plug in these limits. A little bit more writing to do. And if I plug in 1, we have negative radical 2 over 1 plus ln absolute 1 plus root 2. So now we want to evaluate this limit as b approaches infinity. And I'm just going to note, you know, this guy at the end, that's a constant. So I'm not worrying about that. That's not doing anything. It's just staying put wherever it is. Now, as b approaches infinity, our regular algebraic techniques can show us that this is going to approach, and I wrote something wrong here. That should be b to the fourth. Sorry about that. B to the fourth plus 1 in the radical. Our regular algebraic techniques can work on this, or you can use L'Hopital, but you'll see that this fraction approaches 1. As b approaches infinity, this whole argument inside the ln approaches infinity, which means the ln itself approaches infinity. So look, if one part of it approaches infinity, while the others are approaching constants, then that means the whole thing blows up. This surface area is infinite. So, finite volume, infinite surface area. Wow. It was quite a bit of work to kind of get through this. The volume part was pretty easy, but it is sort of interesting, I think, conceptually, that this theoretical thing, the thing that cannot actually exist physically, but that this thing can have a finite volume but an infinite surface area. It's almost like saying, if you could construct a bucket, a container like this, right? You could construct a Gabriel's horn, you could fill it with a finite amount of paint. It could not possibly contain enough paint to paint itself, right? Because its surface area is infinite.